So, and this is, in terms of numbers, it's pretty realistic. And obviously the ground station wouldn't look that big on the Earth, right? But that part is unrealistic. But otherwise, the numbers are pretty good. So, if we're shooting a signal from this station to the satellite to the other side of the Earth, maybe you're talking, like when it says ground station, or it could just be like a satellite phone. Maybe you're talking to somebody over in China or something, right? Through a satellite. So how do you find, using this speed, how do you find the time it takes? What do you have to know first? Like, let's put it back into realistic terms here. If I said, how long would it take you to walk home? If you can walk 2 miles per hour, what would you need to know?
Miles you're walking?
Yeah, you need to know how far it is, right? And then you can do what to get the time? So let's write that. Let's say you're walking 2 miles per hour. That's pretty slow. Let's make it 3. 3 miles per hour. And you live 6 miles away. Okay? So this is the distance, right? That's what you guys said we need to know. And then of course your speed, which for the radio waves is given. So if I said, how long would it take you to walk home, what would you do to get that number with those two?
Divide 6 by 3.
Okay. So she says divide. Kyron mentioned multiply. If we divide 6 by 3, that's 2 hours. If we multiply it, it's 18 somethings.
Yeah.
Okay, so you want to change that? Okay. So you're dividing distance by rate. That will give you time. Okay? So what do you need for this one? It's the same exact idea, but what do you need in order to be able to answer for time?
Distance from the ground station to the satellite?
Yeah. So we need the distance from there to the satellite, and then what?
Back. Like the other ground station.
But what's true about those, based on what we learned yesterday? Yes, why?
Because
It's not that. There are tangents from the same point. Remember that theorem? So if the same point is the satellite, and then their tangent, just kind of skimming by and just touching that one point, the point of tangent. Everybody good? So you just need to find how long one of them is, and then double it. What will you need to find how long it is, though? So this is the part that takes a geometry picture on a worksheet and kind of expands it to real world, because the information isn't already drawn perfectly for you. And this is more like how real world information would be given. Like, how high is the satellite above the Earth? What's the Earth's radius? So how far are those? So how do you find that out?
Can we connect the Earth's radius to the 35, like 100?
Yeah, remember? So the radius is the same all the way around, right? So we could draw a radius here as well. 35, no, I'm writing the wrong number. 6371. Okay? And where else can you put it that would be useful? Right there, right? And then we have that other theorem, which says what? How about Linda? What theorem is working in between these two, the yellow and the blue line? So the satellite signal and then the ground station to the Earth's core. This was 2 days ago. Well, we used it yesterday too. Silvana, help her out. Why did we care about putting that right there? Remember the radius tangent theorem says that that's a 90. Let's put a different color. Okay. Alright, that's all I'm going to say for now. So you need, obviously, the distance, the rate was given right here. And our ultimate goal is to find out time, how long it will take. And you have an idea of how long that should be, I think. Like if it's 20 minutes, you're probably wrong. Right? Okay. You ready?
Yeah.
Alright, well, guys, when you have a problem like this in context, sometimes it's nice to go draw the geometry focus that you're working on. And I think it helps the stuff a little bit more stand out. So there's our 90. And then we had 6371. This was 6371 plus the distance that the satellite is above the Earth. So we'll leave that as a total. And then we want to solve for satellite to ground station. So how do we? Like what tool do we use to do that? Good, yep. So this will be x squared plus 6371 squared. Will you tell me, since you wrote this, what that is? Okay, so these are big numbers when we go to square them, right? So one thing that you could do instead of writing those huge numbers over and over is just keep them written as squared in your work until you're ready to do it on your calculator, okay? So do we all agree to get rid of this? I would subtract it off, the 6371 squared, okay? Which is going to be 42157 squared minus 6371 squared. And I'm putting the square root on there because we want to get rid of that squared, right? We just want x. So is everybody good on where that came from? Okay, so this way I only had to write those twice. I don't have to write any bigger numbers, which is really nice, right? And we can just go straight to the calculator with all that. So 60. Wait a minute. Did I write it wrong? No, I did. 42157 squared. 42157 squared minus 6371 squared is 41673. I'm just going to round it. Now, why is it so close to the distance that the satellite is above the Earth? Like, why is this one's almost 42, and that one's just barely over 42. Why are those close together? Like, did we do something wrong? Well, here's a similar idea. We'll exaggerate it just a little bit. If this was like 2 miles and this was 10,000 miles, what would you expect the hypotenuse to be? Just barely, like fraction, right? I mean, because does 2 miles make up much difference when you're comparing it to 10,000? Not at all, right? So that's what's going on here. The distance from the center of the Earth to the edge of the Earth is a lot smaller than the distance the satellite is out there. So it's not affecting it a whole bunch. So it was 41673 is what we're going to put. Get out of the way. Now, what do we do with that? Oh, that's not miles, that's kilometers. What do we do next, Silvana? Does everybody know where that is in the picture? Okay, where? Yeah, it's this, I mean, if we copy it directly, it's the left yellow line. Okay, so we're shooting the signal from the ground station to the satellite to the other one.
Can't we use like HL congruence to put on the other side?
We don't need to, we just have a theorem that says those are congruent because they're tangents from the same point. So guys, once we have a theorem that says that, we don't have to keep going back through the whole triangle thing, right? Like saying HL, we don't have to do that. That's why they're congruent, but once we have proven that they are, we don't have to keep proving it. We can just know that since they both come from the same satellite, or go to it and then come from it, that those are congruent. They just are. It's tangents from a common point. So we can copy 41,673 here. And now how are we going to find the time? Yeah.
Divided by 3.
Yeah. Okay. So here's how I'm going to do it on the calculator so I don't have to type that in again. I'm just going to hit times 2. And it will bring that previous answer down so I don't have to retype it. Okay, so that is double the distance. It's to the satellite and back down. And then I can just hit divided and enter 300,000. 300,000. That way I'm not retyping these big numbers and having that opportunity to make a mistake, right? You let your calculator store that for you. Okay, so I want you to process this. This is not, again, just some randomly made up problem in math. Here's what we got. I'm going to round it to 0.28. What is the unit on that? This was our time calculation. So what is the label? That's seconds. Okay? So let that sink in for a second. Quarter of a second, like just over, let's say a third of a second, between those two, to go 83,000 miles. That's cool, right? How'd you do? You got it? Awesome. Okay. So, light is super fast. Did you know it can go around the Earth 7 times in 1 second?
Wow.
Yeah, that's no small thing, right? 7 times in a second. So light is ridiculously fast. And why am I saying light when this said radio waves? Any thoughts? Well, radio waves are part of what's called the electromagnetic spectrum. Have you heard of that if you've taken physics? Mm-hmm. So they are the longer wavelength waves of the electromagnetic spectrum, and then visible light is shorter wavelengths, and it's a really tiny part of that whole spectrum actually. But they all travel the same way, which is really fast. In miles, it's 186,000 miles per second. Isn't that crazy? How fast is sound? Sound? No, it's way, way, way slower than that. I know it in miles per hour, but not miles per second, so I'm just going to do that real quick. So it's 750 miles per hour. So it is this 0.2 miles per second. Okay, so compare those two. 186,000 miles versus 0.2 miles. That's way different, right? Have you ever had the opportunity to see something happen before you hear it? If you ever get a chance, it's kind of cool. Like, if you're across a big parking lot, you see somebody shut their door, but you can't hear it, and then a second later or two, it's like, right? Or the most common probably is lightning. If it's 0.2 miles per second, how long does it take to go 1 mile? Yeah, 5 seconds, because 0.2 times 5 is 1. So if you ever work as a lifeguard, or if you're ever around somewhere where it's unsafe to be in lightning, which I guess is always unless you're inside, but see lightning, count 1, 2, 3, 4, 5, and just count. And every 5 seconds, it's a mile away.
Planes also are a really good example. Planes, when they're flying over,
Oh,
you
yeah.
hear them until like.
Well, yeah, and the kind that fly in the air shows, like the fast military jets, can fly way faster than the speed of sound. So it's a tactical advantage. They can't do that anymore. They used to be able to fly. Have you ever heard of a sonic boom? They used to be able to do that, but now they can't. They legally around town they could. I remember hearing it as a kid when I was out on recess. It was cool. But I guess they made that illegal now. Anyway, lots to think about in that one. You like those kind? Kind of makes the math more relevant. Grab that sheet from yesterday and let's continue working on it for a bit. Well, till the end, and then we'll check it till the end of the sheet. But give me an idea of how long that might be. And then, didn't you get through almost the whole front?
Yeah, I only have 2 more.
Okay. You're about there. Kyron, are you close to done with the front?
Yeah.
How about you, Salon? I'm thinking maybe like 10 or 15 minutes. Is that probably good? Let's do it. All right, so it's coming up at number 1. You should have put no, yes, yes on there. Okay, first one. If you copy 51 through the vertical angle, now you have these 2 angles in the upper triangle, and you subtract those from 180, you get 90 at A, and then that means it's not, the question asks, is the bottom one at C, is it less than? Well, they're the same, right? So less than is not the same as equal. So that's a no. Also, we just proved that the angle at A is 90, so that makes BA a tangent. Okay? And then if we do the Pythagorean theorem on, where did I do it? Right here. If we do the Pythagorean theorem with the 4 and the 5, we'll get, and we square root that, we get 6.4-ish. Right? So that's all checks out. Okay, number 2. Doing a perimeter. Okay, remember 5 can be copied it's all 3 of them. It can be copied to the 2 other radiuses shown in the picture. So R to T is a radius, 5 plus 4 is 9. So now we're working on that right triangle, which is 9 squared minus 5 squared. And when we square root that, we get 7.5. Okay? Copy the 7.5, whichever one you decided to solve. Copy it over, because we were told those are tangents. And then we can do the perimeter to get 25. How'd that one go? Okay. Number 3. This is one of those kind we did on the screen yesterday, where we can just use the fact that these are all tangents. How do we know they are? Because this one had no words. These 90s are telling us that. So if those 90s hadn't been there, you couldn't even do this problem. So make sure you know what the notation is telling you. Once you add it up, you get 36. Okay, we'll come back and talk about 4, 5, or whatever number this would be. You should have gotten x equals 8. Just set those two equal to each other. They're both tangent from the same point. Same here on this second number 4. Set those equal, solve to get 3. Okay? Good on those? Backside. We did one like this on the board yesterday, where we had a given long length and we had to subtract something to get the little short bits of it. So like we were told SU was 11, and we had to subtract so that we could break this up into 5 and 6. Same thing here with UW. We were told it was 17, and we had to subtract to break it up into 6 and 11. Otherwise, it was just copying all those little pieces and adding them all up. Which, check this long thing out. If you wrote it out, that's a lot of numbers, right? So you have to just go around and make sure you hit them all. So be careful on that. Finally, this last one is kind of like 4, but a little easier. And it's because the r squareds cancel. So you should have got 6 on that one. Okay, and then zooming back to number 4, your answer, oh, I don't have it on. Your answer was 0 and 8 when you solved, but the 0 doesn't work because 0 can't be the radius, right? So this was a quadratic that you had to factor. Remember, with quadratics, you often get 2 answers. But in this case, one of them doesn't work because, again, it makes that radius 0, and 0 doesn't make sense. How'd you do?